Okay, what we saw in the morning was to show that at least for the erasure case, we had this polarization phenomenon. So the synthetic channels that we created, they approach to these two extremal channels. We'll worry about how fast they do so and so forth later on, but I want to maybe at this moment take a little bit step back and then take a look at what are the synthetic channels that we have created. We have seen this in the BEC case fairly carefully, that the plus of a BEC is still a BEC, minus of a BEC is still a BEC, with erasure probabilities being squared, or this 2p minus p squared. But let's take a look at what kind of channels do we create in the general case. So what we have is, remember this transformation. We have binary input channel. This is the x1 and x2. Each xi is in the binary field. And then what we do is we put this modulo 2 operation in here, call it to be u1 and u2, and we have here outputs y1 and y2. These need not be in any particular, I'm not constraining them to be anything in particular, so they're arbitrary alphabets at this moment. Okay. They could be real, they could be binary, they could be ternary as in the erasure channel, so we don't know anything about this. So now I will assume that these two inputs, u1, u2, are also independent and fair coin flips. So the u1, u2 independent and Bernoulli half. This means that it's a coin flip with probability half of coming to be ones, and of course probability half to be coming to be zeros. So this means that for example, that the values of u1, u2 are 0, 0, 0, 1, 1, 0, and 1, 1, with probabilities quartered each. If u1, u2 is 0, 0, x1, x2 is also 0, 0. If u1, u2 is 0, 1, x1, x2 are 1, 1, I think, right? Because x1 is obtained by summing these two bits, and the x2 is the same as the u2, like that. If it is 1, 0, you get 1, 0 back. If it is 1, 1, you get 0, 1. Okay? So we said x1, x2 is also tracing the four possible values or the bits might take in different order than the u's. Okay? But in particular, the same probabilities apply to distribution of x1, x2 also, namely x1, x2 are also independent and Bernoulli half. So the u's and the x's, they are dependent, of course, to each other, but within the u's you have independence, within the x's you have independence, and the same distribution. So they're both, everything is IID 1/2, whether in the u domain or in the x domain. Okay. All right. Good. So now let's now take a look as to what is this channel W minus we have created. So W minus, the outputs y1, y2. Let's take a look at suppose the u1 is 0, the input is w. Maybe I should remind you as to this. W minus is the connection between u1 to y1, y2. Let's look, what is the chance of the receiving a particular y1, y2 given that the u1 is 0? Okay. Well, given that the u1 is 0, u2 still can be anything, 0 or 1, with equal probability. So the probability half, the u1 is also 0, in which case we are feeding the two channels 0 and 0. Okay? So we are essentially here. u1 is already 0. Okay? We are seeing the channel either 0 or 0, in which case the channel W produces y1 from x1, and the second channel W produces y2 from x2, both of which are 0, 0. Okay? Or, okay, the other possibility is that the u2 is 1. So this is the the chance that the U2 is 1, and so U2 is 0. And when U2 is 0, the inputs to these two channels are 0 and 0. Or it could be that the U2 is 1, again with probability half, in which case we're sending a channel 1 once. Right? This is the, so all I'm saying is that when U1 is 0, with equal probability, we are sending either 0, 0 or 1, 1, depending on the value of U2. U2 can be 0 or 1, in which case these two happens. In this alternative scenario, we have this, and there we have that. Okay. Similarly, at the y1, y2 given 1, so given that the u1 is 1, we are here. So depending on the u2 being 0 or 1, we are feeding these two channels x1, x2, which is either 1, 0 or 0, 1. Okay? So we get half okay, so this corresponds to the u2 being 0 again. This corresponds to the u2 being 1. So we have these things. I hope I wrote them correctly with the I seem to have. So this is the transition probabilities of the W minus channel. Okay, it tells you exactly what is the transition probability W minus in terms of the statistics of the channel W. So far, so good. Okay.
The last one be 1, 1.
This one?
I mean, there's two given things, shouldn't they? No.
No, because the x1 is the XOR of these two things. In this case, the u1, u2 are both 1, 1, which makes the x1, x2 to be 0 and 1. So x1 is 0, but x2 is 1. We are on this line, if you wish, here. Okay. All right. So that's a W minus. And we have the W plus, which is the channel, if you recall, between from u2 to y1, y2, and u1. Okay. So if you ask, for example, what is the probability of observing at the output of this W plus channel a particular combination u1, y1, y2, and u1, given the input is a particular value u2, I'm not going to write this thing in the zeros and ones. I'm not going to write down here many possibilities. I'm going to say, given that you have the u2, the u1 that you receive here can be anything. So it is half, regardless of the particular value of u1. Given the u2, this observation here, u1, is equally likely to be 0 or 1 because it is independently chosen from u2. But now that you have chosen to observe the u1, you know that the first channel, it is being sent x1 is equal to y1 is equal to u1 plus u2. Okay, this is a modulo 2 sum here. And the second channel is sent the u2. Okay, so this is the transition probability of the W plus channel. This half is coming from the probability of the u1 being a particular value u1. No matter 0 or 1, it has probability half because it is obtained by a fair coin flip independently of the u2 itself. But once that u1 is obtained, the y1 and y2 are determined in this particular way. Okay? In fact, y2 is not. It depends only on the u2. But the y1 depends on the u2 and u1 that you chose in this particular way. Okay? All right. Perhaps an example is a good idea at this moment because we saw the BEC. Let's take a look at the BSC. Okay. So the example, suppose W is a binary symmetric channel with crossover probability P. Okay, fine. So W minus, we are going to write down the y1, y2, and u1. Let's write it for maybe, here are the y1, y2 values. And the u1 value, let's say we first set it for the u1 value is equal to 0. Okay. How should I do this thing? Hold on a second. Let me write it like this. W minus of y1, y2 given 0. The possible values are, these are what you might receive as y1, y2. Okay. So what are these probabilities conditioned on a 0 is sent? Okay. If the 0 is sent, either you send 0, 0 across the both channels, or 1, 1 across the both channels. Okay. So to receive 0, 0, there are two things. Either a channel hasn't flipped at all, 1 minus p squared, or both channels flip. Okay, that's the only possibility of this happening. The same thing, by the way, for 1, 1. So if 0 is sent as u1, the x1, x2 are either 0, 0 or 1, 1. If they're 0, 0, here you'll get p squared over 2 plus 1 minus p squared over 2. So this is the same value as above. So we get these. Okay. And here, so 0, 0 is sent with half probability. In that case, one channel should flip, other one should not, okay, to get this one. Or, again, the same thing. One channel should flip, other channel should not. So we have p times 1 minus p in both cases, with the probability half-half added. Okay, and same number appears here. Okay. All right. Good. Let's take a look at what happens for the given 1. Okay, when the u1 is 1, what do we get? Well, these things are exactly swapped, because in this case either 0, 1 or 1, 0 is sent. So to receive a 0, 0, you must have had the case that the one channel flips, other channel does not. So we get the p times 1 minus p here. For this one, either 0, 1 or 1, 0 is sent. So we get this number appears here. Okay. Same number appears there. And p times 1 minus p appears here. Okay. All right. So now what you see at this moment is the following thing. 0, 0 and 1, 1 vis-a-vis the distinguishing whether 0 or 1 exactly the same. Because these two symbols, they're the same probability distribution under 0 and 1, they're the same thing. So this is these two things here. So you can merge these two symbols. So this guy and this guy, they can be merged to a single output. Similarly, this guy and this guy can be merged into a single output also, because they're not distinguishable from each other. Whether you have the 0 or the 1, they're the same probabilities under both things. In fact, what it counts is that the likelihood ratio are the same in these two things. So what you have is this is equivalent to a channel. Let me call this one to be, let's say, 0 prime as a symbol, a channel with input 0 and 1. You have 0 prime and 1 prime. Okay. So if it is 0, you receive either this or this, or one of these. So let me just do the following thing. If you send 0, this 1 prime is received. So let me call these guys to be 1 prime, and these two guys to be 0 prime. Okay. You receive 1 prime with probability p times 1 minus p. And if you send a 1, you receive a 0 prime with probability 1 times 1 minus p. Other ones are the 1 minuses of these things, which is exactly this p squared plus 1 minus p squared divided by 2. So W minus is a BSC, okay, with a crossover probability p into 1 minus p. Okay. So W minus so if you start from a BSC, the minus channel is also a BSC. Okay. So even though it appears to have a larger upper alphabet to begin with, it in fact is the equivalent to a channel with a smaller output alphabet. Okay. What about the W plus? Okay. It's going to be something more ugly there. So we have here now y1, y2, u1. And I shall put here W plus of y1, y2, u1. Given that the u2 is 0, I should also compute the y1, y2, u1, given that the u2 is equal to 1. It's a longer table because it has 8 things possible. Okay. So this could be all right. Okay. So we have from the u1 we get a half already in each of these things. Let me do this one first. Okay. So u1 is equal to 0 with probability half regardless of the value of u2. But now that the u1 and u2 are both 0, this happens with 1 minus p squared. Okay. All right. This one is half. Now the u1 is 1. The channel is being fed 1 and 0. So we get 0, 0 with probability p times 1 minus p. Okay. Here, u1 is 0 again with probability half. That's all right. Okay. So we are sending the channel at this moment 0 and 0. Okay. If we send 0 and 0, what's the chance of getting 0 and 1? It's the same as this. Okay. Here we have u1 is 1. Given that u1 is 1 and u2 is 0, we are sending 1, 0 across the channel. We ask to receive 0, 1. This is now p squared because of this. We are back to sending 0, 0 because of the u1 being 0. We want to receive 1, 0. Happens with probability p times 1 minus p. Now we have 1 again. So we are sending 1, 0. We want to get 1, 0. Okay. This is 1 minus p squared. Okay. This is 0, u2 is 0, so we're sending 0, 0. We want to get 1, 1. This happens with probability p squared. Okay. And then now the u1 is 1, u2 is 0. We are sending 1, 0 across the channel. We're going to get 1, 1. 1 minus p. Oof. Sorry. Okay, I'm really doing a somewhat stupid computation, but it's just to make sure that we get our hands wet. Okay, with this, hands dirty. I guess feet wet. Okay, hands dirty. Whatever. Now, same thing for u2 is equal to 1. Okay. If u2 is 1 and u1 is 0, we are sending 1, 1 across these two channels because the x1 was the summation of the u1 and u2, which is 1. x2 is equal to u2, which is also 1. And we wish to get, we are asking to get what is the chance of getting a 0, 0 as the output. So both channels should flip. Okay, all right. Now, u1 is 1 at this moment. u2 is also 1, so we're sending 0 and 1 across the channel. We ask to get a 0, 0. We get that. Okay. We are back to sending the same thing as we sent here. It was a 1, 1 that we are sending. We asked to get a 0, 1. 1 minus p. Okay. Here, we are sending 0, 1 across the channel because u2 is 1, u2 is 1, u1 is 1. So we're sending 1, 0. We asked to get 0, 1. Did I do it correctly? Sorry, now I'm getting. So here we are sending 0, 1 across the channel. Okay, all right. We must make 0, 1. This is 1 minus p squared. Okay. This is now 1, 1 again. As you get 1, 0. 1 minus p. I should also get my lines to be correct. I should maybe put a line in here so I know that I'm not drifting down too much. Sorry. Here we are sending 0, 1. We ask to get 1, 0. P squared. Okay. Here we're sending again 1, 1. We ask to get 1, 1. 1 minus p squared. Okay. And here we are sending 0, 1. Ask to get 1, 1. 1 minus p. All right, good. Again, now we see that there are similar symbols. So for example, this guy here, okay, and this guy here are exactly the same, okay, regardless of the, they behave exactly the same way under the 0 and 1. Okay. Similarly, if you take a look at this guy here, okay, it is the same as this guy here under the same two values. So the star and the star can be merged, and the double star and double star can also be merged with each other. And similarly, all the remaining stuff, they're also exactly the same. So this triple stars, all these triple stars can also be merged with each other. Okay? So what we have is the following. If you now take a look at this W plus in the W plus is equivalent to, you have 0 and 1 at the output. And you have three symbols at the output, 0 at the input. Okay? And you go from 0 to star with probability, which is the sum of these two things, so which is 1 minus p squared. Okay? It's the same as going from 1 to double star, 1 minus p squared. Okay? From 0, you might go to double star with probability half p squared plus half p squared, which is p squared. Same happens here. Okay? And then from 0 and 1, you can go to the triple star. And these happen with probability. I'm supposed to add the lines which correspond to here, 4 of them. So there is 2p1 minus p. Okay? So this number here is 2 times p times 1 minus p, which is exactly 1 minus the summations of the 1 minus p squared and p squared. Okay? So remaining, this thing is labeled by 2p1 minus p, and the same label here. Okay? So, sorry, I'm writing too small perhaps, but hope you can see, because these numbers should add to 1, and they do because of the expansion of p plus 1 minus p quantity squared. Right? All right. So what you get is a mixture between the symmetric and the erasure channel. So you see, at this moment, while W minus has remained to be a BSC, W plus is not. It has become something which is more ugly. Okay? It has a output alphabet which is not 2 anymore, but 3. So, okay? And now if you take a look at the, so the plus of this is now easy because this is a BSC. We can figure out what is the minus and the plus of the W minus. It's the same computation we had there. But this one is going to get even uglier because if I take the minus and plus of this, we get even bigger output alphabets from that point on. Okay? All right. Is the example clear? How do I do these stars? Okay, excellent question. So now, if you take a look at these two outputs, okay, they are statistically identical under both the inputs. Okay, so input 0 and the input 1, they give this guy these values, and these guys and this guy these values, which happen to be the same as the first row. Because of this, these two outputs, they don't differentiate each other. So whether I have the one or the other, it doesn't make a difference. I know the same about the input. I have the same information about the input, regardless of these two things. Let me say the following. Okay, I have a better answer to this. Okay, all right. So let me do the following thing. Take this channel here. Okay, I'll now do the following experiment. I'll receive the star, okay, and then I'll make a coin flip, and then map this thing into with probabilities half into 0, 0, 0. Okay, and what was the other one? The 1, 0, 1. Okay, I'll take a double star. I'll also take a coin flip here. Okay, and I'll map it into 1, 1, 0 or 0, 1, 1. I'll take this one and take a four-sided coin with probability quarter each, and I'll create the remaining outputs. I forgot what they were. 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. Now, if you take a look at what is the transition probabilities from here to here, you will find exactly this table that we have here. Okay. So what is the chance of getting an all 0? Well, to get to all zeros, I need to first get the star with probability 1 minus p squared. And then with probability half, I generate this all 0 sequence. Okay. So you see that with this channel here, this channel with the three outputs, the star, double star, and triple star, I can simulate your original channel. Right. So this, I can simulate W plus with the smaller channel, because this channel, overall channel here, has the same statistics as the one there. Are we okay with this? I think not. Are you sure? Let's go this thing once more. So take a look at this diagram here, and let me ask you, what is the chance that, given that I send a 0, I'm going to receive a 0, 0, 1? Okay. The only way to receive a 0, 0, 1 through this is to first get a triple star, okay, and then with quarter probability take this particular branch here. Okay. This happens with probability 2p1 minus p times a quarter, but is exactly half p1 minus p. Okay. So which is exactly, magically enough, this number here. Okay. So this overall structure completely simulates, or is completely equivalent to this big channel with 8 outputs completely. Okay. So the small channel here can simulate the big channel. At the same time, the big channel can simulate the small channel, because I'll do the following thing. I run the big channel. Okay. If I observe a 0, 0, 0 or 1, 0, 1, I'll declare a star at my output. Okay. So since these two channels can simulate each other, they must be equivalent. Okay. So with a small channel, I can simulate for you the channel with larger outputs, and from the channel with larger outputs alphabet, I can simulate the channel with the small alphabet. Consequently, these two channels are as powerful as each other. Whatever you could do with one, you could do with the other. Okay. That's the meaning of channel equivalence anyway. So I call two channels to be equivalent if channel A can simulate channel B, and channel B can simulate channel A. What do you think, Dan? This is a terrible way to explain things. Sounds good to you. A somewhat more sophisticated explanation would be the following thing. For binary input channels, a sufficient statistic is the likelihood ratio. Okay. So when you look at you receive a channel output, you simply compute the ratio between the probability of this output given 0 divided by this output given 1. Okay. Now, if you then take a look at these symbols star and the star here, they are the same likelihood ratio. The ratio between this value and this value is exactly the same as the ratio between whatever, this value and that value, because they happen to be the same in this particular case. Or for the triple stars, likelihood ratio is exactly 1, okay, and so forth. Okay, so this is if you want to look at log likelihood ratio and so forth. So symbols with the same likelihood ratios, they can be merged, because that's the only statistics which counts. So if you want to do anything, the sufficient statistic at the channel is the log likelihood ratio. Okay, but all these concepts are equivalent. It's also a semi-miracle that we got the numbers here correct, because I always make mistakes whenever I make these long tables. If you write 16 numbers down, okay, one of them is going to be wrong for sure. Okay, so it won't happen again. I can guarantee you. Next time you do this table, there's going to be a mistake. Pay more attention. So this time you got easy. Okay. Sometimes this kind of structure is called BESC, erasure and symmetric channels, because this triple star symbol is like an erasure because it has the likelihood ratio of 0. Given this output, the two inputs are equally likely, so it's like being an erasure. Now let's take a look at a few properties of this transformation. Okay. Let me put a small notational thing. I think we're all in the lectures on information theory given in the past week. So you have heard things like entropy, mutual information, and so forth. They're okay. Chain rules, etc. Okay, amazing. Okay, great. So now, let us now take a look at the following thing. So remember what we have here. We have this picture here. We have U1 and U2. identical, independent, and fair coin flips. X1, X2, which are derived from U1, U2 in this way, which are also independent and fair coin flips. And we have Y1, Y2 generated from X1, X2 independently of the other. So Y1 is generated only from X1, Y2 is generated only from X2. Once X1, X2 are given, Y1 and Y2 are independent of each other. Okay. So let's now try to write down the following thing. So remember, recall, maybe I should say here properties of the polar transform. So let me write down So let me just start with this quantity here, okay, and observe the following: that x1, y1 is independent of the pair x2, y2, because these are just x1 and x2 are independent to begin with, y1 dependent only on the x1, y2 depend only on the x2, so these are independent quantities. Okay. In fact, they're the same distribution too, because x1, y1, x1 is a fair coin flip, y1 is obtained by passing x1 through w, x2 is a fair coin flip, it is y2 is obtained by passing x2 through through channel w. So these are the same. This is 2 times any one of them. Okay. All right. But it's also equal to x1, x2, and y1, y2, because the distribution is a product distribution. So the additive properties of the mutual information guarantee you this. Okay. Now, x1, x2 is in one-to-one correspondence with u1, u2. This one and this one, they determine each other. So from a mutual information point of view, whether I start with x1, x2 or u1, u2, they're the same information. So, okay, so this is the same stuff. Okay. And now let me use chain rule on this guy. Okay. u1 semicolon y1, y2 plus the u2 semicolon y1, y2 given u1. This is the chain rule of mutual information. Whenever you have multiple objects here, some object here, I can always expand the mutual information as between the first and the output, second and the output given the first. Okay. This. Now, in the meantime, this guy is the same as the I of the u2, y1, y2, u1. And why is this? Because of the following. I can add here a 0, since u2 and u are independent. This is nothing I'm adding. This quantity is 0. But these two things is the chain of expansion of this. I of u2 semicolon u1 plus I of u2 semicolon y1, y2 given u1. Okay? Okay. Is this okay, or am I... You're happy, but anybody else? Essentially, I just added here something which is 0. Mutual information between independent random variables is nothing, but it allowed me to recognize these two terms as the expansion of this thing by the chain rule. Okay? As u2 and this guy, and u2 and the other guy is given the first guy. Okay. All right. Okay, good. So now, let me give this thing a name. This is the mutual information across the channel W minus. W minus is precisely the channel with input U1 and the output Y1, Y2. Okay. Let me call this thing with an abusive notation I of W minus. So I of a channel, as opposed to putting here some x's and y's, I of a channel, it means the mutual information developed between the input and the output of the channel when the input has the fair half-half distribution. So, okay, so the I of a notation, I guess I should maybe write down here. I of W, this is the I of the input of W semicolon output of W when the input of W is Bernoulli half, okay? Because when you ask for mutual information, I should give you a complete distribution. What is the distribution of input, and what is the channel which connects the input to the output, okay? So by this I mean the following. So consequently, this is I of the W minus synthetic channel. And this guy is, this is the input to W plus. This is the output of W plus. Which one? Second one is I of W plus. Thank you. I of W plus. And this one is 2IW, because x1, y1 is the input of output channel W, so is the second term. Okay? So what we have is, we have obtained the following relationship: conservation of mutual information by the polar transform. The created channels, W minus and W plus, the mutual information is developed across them. If you sum them up, you are no more and no less than the original mutual information of the two channels that you started from. So, okay, so the property 1, 2I of W is equal to this. Okay? This is very much in the spirit of for the BEC, the erasure probability was conserved. Okay, the two synthetic channels had erasure probabilities whose average was the erasure probability of the original channel. And there's a special case of this because for the erasure channel, the mutual information is nothing but 1 minus the erasure probability. So if you want, this was for the binary erasure channel case. This number was twice 1 minus p is equal to twice 1 minus p into, what am I saying? 1 minus p, 2 minus p plus 2 times 1 minus p squared. This is the erasure channel case, which is the same thing as saying that the erasure probabilities are conserved. Okay, so it's not relevant. It's just a corollary of. So we could have. We didn't have to compute erasure probabilities. If you had computed one of them, the other one would have been obvious because of this observation here. Okay, so we had this. Okay. Now, secondly, I take a look at the I of W plus here. Okay. Now, so this guy here, the mutual information between U2 and all these three things, this is clearly bigger than the U2 and any one of them. Okay, so if I remove some things from the output, okay, I can't get any less mutual information because this is how much information does these three things tell me about U1. Well, okay, if I throw away some of these things, I must be reducing mutual information. But U2 is nothing but X2. This is the same as the X2 and Y2, which is the same as I of W. Okay? So IW plus is more than IW. Okay? So this notation of plus is justified by that. So the plus channel has always more mutual information developed across it than the W itself. Okay? So the IW plus. But if IW plus is more, IW minus, can it also be more than IW? If it were, you would never get this, okay, because their sum is conserved, so this one must be then less. Okay? So the IW minus, IW, and IW plus must be in arithmetic progression, because this middle one is the average of these two, okay, and one of them is smaller, one of them is bigger. Okay, that's it. So these three objects are in equally spaced. IW, IW minus, and etc. Okay. So we have this property here. Okay. Yes, sir. then things will be very different. Yes. Then I could not write a chain rule for you. But fortunately for us, when the U1 and U2 are independent and fair, okay, then X1 and X2 are also independent and fair. Okay. If I had either made U1, U2 correlated, or if I made any one of them to be biased, then I would be introducing correlations among the X1 and X2, and I would not be able to write any of these things down. So this would have failed, okay, because you would no longer have independence. Okay, this will still be okay. This is fine, regardless. Okay, this is also fine, regardless. But this would not be 0, depending on if the U1 and U2 were correlated. I could not have added this particular I of U2, U1. I could not have added there because I'm adding a 0, I claimed, but it would not be. So all these things would get messed up. Okay, so this independence and fairness of the U1, U2 is crucial to this derivation that we have.
Maybe I'm not remembering this because it's been erased, but it seemed to me that W minus was a better channel than W. It had a smaller...
No, that's the one with the W plus had the squared erasure probability. If you take a look at the erasure channel, it was the one who was...
W plus had the 3 outputs.
W plus had the 3 outputs. One of them was an erasure.
This was just a BSC.
BSC with a much higher crossover probability.
I thought it was smaller.
That's what I wrote, you're right. But cannot be. Must be 2p1 minus p. So I must have made a... Okay. Let's take a look at the W minus derivation. When I merge these two things, it should have been 2p times 1 minus p. Right. Because if the original channel had p is equal to half, the W minus should also have...
Because I thought that W minus would be the bad channel. Yeah.
It certainly should be. Sorry about that. But so this computation W minus C, I mean, a mistake was made before. So the big table was wrong, but the small table was, I think, also correct. But when we merged the two symbols, we had merged two symbols with probabilities, both p times 1 minus p. When we merged them, of course, we had to add their probabilities too. So it should be 2p1 minus 2p times 1 minus p. In particular, for the case p is equal to half, if the original BSC was completely terrible, it was flipping with probability half, nothing that you create from it can have any positive mutual information. So consequently, W minus must also have probability half. So 2p1 minus p equals a half when p is equal to half, whereas p1 minus p will be a quarter. So there is something terribly wrong with that formula. Okay. Now, the other thing is the following. The third property, I want to take a look at, just as we took a look at the difference between the worse and the better erasure probabilities for the BEC, I want to take a look at the difference between the mutual information developed across the better and the worse plus and the minus channels. Okay, and I want to take a look at this thing vis-a-vis the mutual information of the original channel. Okay. So this is a number between 0 and 1. Okay, the original mutual information. Okay, and the question as to what might this difference between the two mutual informations of the synthetic channels might be. Okay. So one thing you can do is the following. You can randomly generate channels. Okay, so take a output alphabet, let's say size 5. Okay, fill in a table of W of y given 0, 5 values for this, which add to 1. Randomly pick values for W of y given 1, which add to 1. Okay. Compute for this thing, I of W, compute for the W plus channel, compute IW plus, compute IW minus, and then you'll obtain some value here. Compute the difference between things that you compute. Okay. Make another experiment. Okay. You'll obtain a whole bunch of values that are in here. Okay. You will notice fairly quickly on that what's happening is this. We'll end up with, in a crescent-shaped region, is where these two values, on the x-axis IW, on the y-axis the difference between IW plus and IW minus, you will find that all these things are filling in here. Okay, And, okay, what you also notice is the following thing, that the upper part of this curve is traced with the family for the BECs. Okay, so this if you go over all the binary erasure channels, okay, you will find the values which are appearing on this top part of this crescent-shaped region, and the lower curve is being traced with the W's, which are the BSCs. Okay, so the BSCs will trace out the lower part of this one. Okay, we will prove this, that this is indeed the case. Okay, no matter which W you pick, okay, the mutual information plot like this, the IW on the x-axis, and the difference of the two mutual informations of the good and the bad channels on the y-axis, it will fall into a line between what was given by the BSC and the BEC channels. Okay? I state this at this moment without proof, okay, but the diagram is like this. At some moment we'll prove it. Okay, the remaining 6 hours that we have, okay, we shall go through this at some moment. But the important property is the following. Remember, to prove that the polarization happens for the binary erasure channel case, the only fact we used was the following, that if the erasure probability, which is not IW here, is away from the extremes, okay, then the difference between the new erasure probabilities that you created was something positive, something which is non-zero for sure. Okay? So here we have the same thing. So this business with this I says that if IW is away from the extremes, then the difference between the new channels, the difference of the mutual informations of the new synthetic channels, is also bounded away from zero. Okay? So recall that for the erasure case in the previous lecture, if the P was between delta and 1 minus delta, implied that the P minus minus P plus was at least 2 delta 1 minus delta. Or I guess we had stated it in the half. We had stated like this one. If the erasure probability of W is between delta and 1 minus delta, the synthetic channels that we create has erasure probabilities P minus and P plus, whose difference was at least this. Okay. We had the same situation here. If IW, so this is between delta and 1 minus delta, then half of the difference between IW plus and IW minus is at least some function, let's say kappa delta, which happens to be positive, okay, kappa delta away from zero, with a kappa delta, I'm not sure why I call this in kappa, but anyway.
This is W plus?
Which one? This term here is W plus, because it has the bigger mutual information. So, whereas the erasure probability and the mutual information are exactly opposites of each other. So, bigger the erasure probability, lesser the mutual information. So, I wrote this thing with the minus minus the plus, okay, of the erasure probabilities. Here I write the mutual information of the better channel minus the mutual information of the worst channel, so that I get a positive quantity on the left-hand side. What I claim is that if IW is far away from this, then this difference, this inequality which I create in the one stage next, is at least something with a kappa delta for some. Maybe let me write this down here, okay, so people can see this. I'll copy this one here. So the property 3 prime, which is a corollary of this graphic, there exists IW implies that the IW minus divided by 2 is at least kappa of delta with a kappa of delta which is strictly positive whenever delta is positive. Yes, sir.
Does this mean
So this is essentially saying, in one step, how much inequality does the polarization create? Okay. So this will, bigger this, the faster you are separating. Okay. This is a guaranteed progress property because, for example, if you have BECs, the kappa is even bigger. Okay. So this is saying that no matter what your channel is, there is some progress towards inequality. Okay. That this is maybe a complete misnomer, but okay, so, people typically want equality, but okay, here we are trying to progress towards extremes. Okay. You make some positive progress. Okay. So this I call, let's say, the guaranteed progress property. So if you are not polarized yet, you will have some polarization happening. Okay? If you're already polarized, okay, if your channel has already zero mutual information or full mutual information, then of course you make no progress because you're already there. So you never destroy polarization. Indeed, I mean, if IW is 1, this guy cannot be more than 1. It's a binary input channel. Consequently, this guy also must remain at 1. So once you arrive, you remain. Okay? So these 0 and 1 are trapping points for the evolution of IW. The two extremes are trapping. Once you reach there, you cannot leave because there's no way to move. If you're at 0, this cannot go below 0, so it remains at 0. Consequently, this also has to remain at 0 to satisfy the average. So this and the top and the middle two guarantee that the progress once you arrive at the extremes, you remain there. And this one says that if you haven't arrived at the extremes, you go towards it. Okay. All right. So now, if you take these things to be granted, okay, we haven't proven this tree yet at all. So I haven't shown you given a proof of this. At this moment, just believe me that this property 3 prime holds. Once you have this, you can follow exactly the same steps as we did for the BEC case to show that polarization happens for arbitrary channels also, but for the same reason that the polarization happens for the BEC. Because what you do is you would write down the following thing. You would start with, instead of remember we had these tables whose columns were the erasure probabilities of the channels created after I steps of polarization. I have the same table, but instead of erasure probability, I had a mutual information. I have a table with IW. Here I'm going to have IW plus, IW minus. I'm going to have here IW plus plus. Like this, okay. And I'm going to compute again 2 statistics. One is the arithmetic average of these columns, okay. Because of this property here, just like the erasure probability being preserved, it will guarantee that the arithmetic averages remain constant. So you always have the mu0 is equal to IW, mu1 is equal to IW, mu2 is equal to IW. That will not change. Okay. And then I'm going to compute the sum of the squares of each column divided by the number of items in each column. I'll obtain these nus. Okay. Nu0 is IW squared. There's nu1, which is the average of the squares of these two guys, and so forth. And for the same reason that we have here, these nus are going to be, again, an increasing sequence. Okay. And since they're bounded between 0 and 1, they also converge. Consequently, difference between the successive nus has to go to 0. And difference between successive nus is lower bounded by kappa delta squared times the fraction of unpolarized channels. Consequently, for the same reason that the number of unpolarized BACs goes to 0, the same is true for in the general case also. So at the end, no unpolarized channels are left. So this diagram that we saw for the BEC is generic. Okay. I'll write this thing down more carefully maybe tomorrow because I think we are 2 minutes before the end of this lecture. So I don't want to write down this, but I guess you see, if you follow the BEC proof, you will see that the same machinery will exactly prove that once you believe this property here, once you believe this 3 prime property here, okay, if you take this for granted, we'll get the same proof for the general channels as we had for the BEC, that the fraction of polarized channels go to 0. Consequently, the fraction of good channels for which IW is close to 1 has to approach the I of the original channel that you started from, and the fraction of polarized channels whose mutual information is close to 0 has to approach 1 minus the mutual information of the original channel that you started from. So at the end, you get exactly the correct number of good channels to transmit over. Perhaps the reason that you asked me this question about correlated X's was because of the following. You were thinking maybe of a channel W whose capacity is achieved not by the uniform distribution Bernoulli-Huff, but by a different distribution. So at this moment, what we have done is we have achieved the capacity, not capacity, but achieved the, for lack of a better terminology, I'll use what Erdala said, symmetric capacity. Okay. So namely, the mutual information evaluated for the uniform input distribution, the Bernoulli-Huff distribution. At this moment, we're only achieving rates up to that number. If you have a channel whose capacity is indeed achieved by the uniform distribution half-half, such as any kind of symmetric channel, then you're already there. Okay. If not, we are not at capacity yet, but let's not worry about this at the moment. Okay. So, questions so far for the first day? Sir?
How times I have W plus 2?
Oh, this one being bigger than that. So I haven't given any intuition at all. Okay, that is, at this moment, I've simply stated as being a fact, okay, that when you do this plot, okay, and if you just make a whole bunch of trials, you will find that every point that you put lies inside this crescent. I also make the claim, completely unfounded at this moment, that the lower curve of this crescent comes from the family of the binary symmetric channels. These are the, in a sense, least polarizing in one step. Okay, so if you ask how much progress towards polarization do you make in one step for among all channels of a given mutual information, the BSC is the one which makes the least amount of progress, and the BEC with the same mutual make the most amount of progress towards polarization. Okay. Of course, the BEC after polarization remains a BEC, so it keeps making the fastest progress is made by the BEC because it remains on the top curve all the time because the BEC remains a BEC. But the BSC doesn't remain a BSC, so it makes slow progress, but at the next step, the W plus of the BSC is not a BSC anymore, so it's making slightly faster progress than what you thought. So but the minus side remains a BSC, so it's still making slow progress. But at some moment, they also begin to make faster progress too. But regardless, I mean, everybody is making some progress. There's nobody here which touches 0. Okay, there's nothing. If the curve was like this, I would not be able to prove you anything. Okay, but fortunately for us, this curve that is here, it never touches the x-axis except at the two extremes. Okay.
Given a channel,
yes, sir.
are there any other polarizing transform which will maximize the kappa? Are there results, for example, to say, okay, this is the best kappa and this is the transform that will achieve that?
Nice question. So if you have binary input channels, okay, first of all, to be able to preserve mutual information, because if you lost that, then you are doomed. Okay, so you had a one-to-one transform in here. Okay, so the U1, U2 must determine the X in a one-to-one way. There are not too many of these things possible. Okay, you try them, and this is the only meaningful one. Okay, so okay, you do trivial things like you first complement the U, okay, and then do the same thing, or complement the U2, do the same thing, or you do it the other way around, that you put the plus sign here and so forth. Okay, and all these things are the same transform. At the end, the only meaningful way to do anything is in fact this one. So for the binary input and combining two case, the answer is no. Okay. But if you had for example, a bigger input alphabet, okay, and you were trying to put here some operation which will preserve one-to-oneness, then one can examine this question. First of all, one can first ask, what are the polarizing operations that you could do? Which ones will lead to polarization to begin with? Maybe some of them, they get stuck. Okay. So I have a student, Rajai Nasser, Lebanese guy, very sharp. Maybe I should not be saying this thing on the video because he's a remarkable fellow. Like my other students too, but okay, that is. But he has some very nice results on exactly telling you which transform polarize, which one will not. He has a algorithmic criteria which will decide, you give me a function on some alphabet, Will this polarize? Yes, no. You can tell in finite amount of computation time. And he has this very nice algebraic structures and so on, which lead to this somewhat surprising results. Other questions? Sir? This property holds for any channel. This thing that we have here is true over all binary input channels. No symmetry is necessary. But of course, the input distribution is generally 1/2. So I'm not claiming this property for. Actually, it's not even clear what will be the meaning of this if you don't make the input distribution to be symmetric, because this whole, even the mutual information preserving property depends crucially on the fact that this U1 and U2 are independent and fair coin flips. So this diagram applies to symmetric input distributions, but the channel need not be symmetric. Okay? So channel may not be symmetric, but I insist on using whatever channel you give me with probability half 0, probability half 1. Not enough. So we had to know a bit more about this thing than to show that this is not quite sufficient. Okay. Partly because the slope here is not good enough. Okay, so there's a reason for this. Okay, to prove that.
And this mutual information approach
Yes.
works for the erasure channel too.
Of course, yes. Of course, yes. I just want to do the erasure channel first because I think it was something that we can all get our teeth on easily. I didn't use this notation. So everything is just 1 minus all the axes are flipped from left to right, but